Right, in this session we're going to talk a bit about combinations and then apply them to more general counting questions. So we'll call this counting, permutations, and combinations. I'm going to start with the combinations part of this because we haven't talked about that a whole lot yet. Although you might recall my saying that in permutations order matters and in combinations order doesn't matter. So I'm going to start by asking a question. If I've got the letters A, B, C, and D, how many permutations of 3 letters can I make? And how many combinations of 3 letters? Now the permutations we've already dealt with a little bit. What I'm trying to do is from a group of 4 pick out how many permutations of 3 things I can have. So, just going to add a little bit. From the formula, that would end up being 4 factorial over 4 minus 3 factorial, which is really 4 factorial over 1 factorial, which works out to 24. Combinations, we've got to think about it a little bit more, but I'm going to start by listing out what these 24 permutations are. So I could have ABC, ACB, BAC, BCA, and then CAB, CBA. I could have ABD, ADB, BAD, BDA, DAB, DBA. I can have ACD, ADC, CAD, CDA, DAC, and DCA. I can also have BCD, BDC, CBD, CDB, DBC, and DCB. 24 different permutations of 3 letters taken out of that group. But what you might also notice is that these are all the same 3 letters. They're all ABC. These are all the same 3 letters, ABD. These are all the same 3 letters, ACD. And these are all the same 3 letters, BCD. So in these 24 permutations, there's really only 4 different combinations. And what happens is that when you count permutations, you end up overcounting repetitions of the same letters. It's an overcount for combinations. So effectively, in this case, it would have been the 24 permutations divided by 6 to get the number of combinations. But why 6? Because how many ways are there to arrange these 3 letters? 3 ways to pick the first one, 2 ways to pick the second, and 1 way to pick the third, or 3 factorial, or 6. So what I have to do is take the total number of permutations and divide it by how many permutations of the group there are. So what that looks like a little bit more generally is if I have NCR, or N choose R for combinations, and that's going to equal NPR divided by R factorial, because that's how many ways there are to rearrange that small group. if I fill in my values, what I end up with is n factorial divided by n minus r factorial. And that tells me how many different combinations of a group of R I can take from a group of N. And I put that a little bit more detailed. Number of combinations of a group of size R that can be taken from a group of size N. So it's used in much the same way. The permutation one is just, it's for combinations, with the only difference being this factor of R factorial in the denominator to account for this overcount that happens here when you get permutations. So now we're going to look at a few examples of using this generally, as well as when you might get combinations of the two when dealing with a counting question. One other thing that I'll mention notation-wise, you will sometimes see this written in your book like this, and that's just another way of writing the combination statement. Okay, a few examples, and by the way, this work we're talking about today is covering sections 4.5 to 4.7 in your textbook. So, example time. This is example 1 off of page 273. We're asked to determine the number of 3-person teams that can be formed from 9 volunteers. So now that we've talked about both combinations and permutations, when you've got one of these questions, a counting question put out to you, one of the first things you ask yourself is, does the order that I choose these elements in matter? If the order does matter, you're dealing with permutations. If the order doesn't matter, you're dealing with combinations. So in this case, the number of 3-person teams that can be formed from 9 volunteers, it doesn't really matter the order that I choose the 3 people in. They're still going to make up the same team. So since order doesn't matter, this is a combination question. Number of 3-person teams from a group of 9 volunteers is a combination, and specifically I want the number of combinations of a group of 3 out of a group of 9. Your calculator does have this option on it, and if I go into math, ooh, that is really, really dark. Hold up. It's helped not at all. I'll come over here a little bit. It's a little bit better. If I come over to probability, notice my third option down is NCR, and I put 9 and 3, and I get 84. I could also work that out from the formula, and that would be 9 factorial over 9 minus 3 factorial times 3 factorial, or 9 times 8 times 7, which is what this would leave me with, over 3 times 2 times 1. Or 3 times 4 times 7, or 84. Either way is fine. 84 3-person teams could be made. Example 2, page 275. We have a restaurant that has 10 flavors of ice cream. Danielle has ordered a large sundae with 3 scoops of ice cream. How many different ice cream combinations does Danielle have to choose from if she wants each scoop to be a different flavor? Doesn't really matter what order they put these in. So this is another combination question, and it'll be 10, choose 3. If I work that out on my handy dandy calculator, 10 choose 3 comes out to 120. And there are 120 different combinations for Danielle to choose from. Sometimes there's a little bit more involved than just that. So let's take a look at example 3 on page 276, where we have Tanya, who's the coach of a pole push team that consists of 9 players, 5 male and 4 female. In each competition, teams of 4 compete against each other to push their competitors out of a circle. The team that is successful wins. How many different 4-person teams does Tanya have to choose from for an all-male competition? So there are 5 males, 4 females in this grouping. So for an all-male team, there are going to be 5 choose 4 combinations. 5 choose 4, I think we're going to find is going to work out to 5. Five different teams possible. And now part B, we're going to break this down a little further. Part B says how many different 4-person teams does Tanya have to choose from with 2 males and 2 females for a mixed competition. So there are 5 choose 2 ways to pick the men, but that still leaves 2 slots that need to be filled by women. So if you've got to have 2 males and 2 females, if we think back to the fundamental counting principle, that's a multiplication sort of deal. How many ways are there to choose the 2 males? 5 choose 2. How many ways are there to pick the 2 females? 4 choose 2. So we have to multiply those together in this case. And you'd end up with 5 choose 2 times 4 choose 2. Or 60. 60 different teams possible. Right. Keep going with examples. That's what most of this discussion is going to be. Example 4 off of page 278. Planning committees to be formed for a school-wide Earth Day program. There are 13 volunteers, including 8 teachers and 5 students. How many ways can the principal choose a 4-person committee with at least 1 teacher? 4 people, at least 1 teacher. And this you've got to sort of break up into cases. Case 1 will be 1 teacher, 3 students. And that's going to be 8 choose 1 times 5 choose 3. Case 2, 2 teachers, 2 students, would end up being 8 choose 2 times 5 choose 2. Case 3, 3 teachers, 1 student. It's going to be 8 choose 3 times 5 choose 1. And lastly, case 4, 4 teachers, those students. That's going to be 8 choose 4. And you could write this as 5 choose 0 if you wanted to, and it would still work out fine. Or you could just leave it as 8 choose 4. Either one gives you the same thing. Now, you might notice that what we've done here is we've listed out every possible case that meets the criteria we're given. A 4-person group with at least one teacher. These are all the different possibilities that meet that criteria. And so, these are all convenient things we can work out on our handy-dandy calculator. That is really bright. A little bit better. Okay, so I go to math, go to probability, bring out the combination option, 8 choose 1, times, and bring that out again, you get 5 choose 3. 80 for the first case. Now I can go through all that again, or I can just do second entry to bring up the last entry and change that to a 2, and that to a 2. Excuse me, 280. Once again, changing just those two numbers. And then one more time. By the way, if you work out 5C0, you're just going to get a number of 1. So just 1 times 8 choose 4. So then, there are, and I'd have to add all these up. 280 plus 280 is 560, 660, 710. There are 710 different groups that meet the criteria. Now that we've talked a bit about combinations, I'm going to do a few examples which have some combinations, have some permutations, have some neither. And some of the different tools that we've talked about to this point. This is up into section 4.7 now, and this is example 1 off of page 284. Where we have a piano teacher and her students are having a group photograph taken. There are 3 boys, 5 girls, and 1 teacher. The photographer wants the boys to sit together and the girls to sit together for one of the poses. How many ways can the students and teachers sit in a row of 9 chairs for this pose? So, first question, does order matter? Well, yes. Placed in a different order, you'd have a different pose, different people, all that sort of thing. If order didn't matter, there'd only be one way to do this, just one with everybody in it. But the order does matter in this case. So let's think of our groups this way. Teacher, girls, boys. So my first group will be one of 3 possible choices. My second group, one of 2 possible choices. My last group, just 1 choice. That's how many ways you can say which group is going where. Teacher could be in any of these spots, girl could be in any of these spots, boy could be in any of these spots. So there are 6 ways to arrange the 3 groups. But within each group, there's 1 way to arrange the teacher. The 5 girls, there are 5 factorial ways to arrange them. And with the 3 boys, there's 3 factorial ways to arrange them. So in order to take a picture, in order to line up for a pose, you've got to have the 3 groups arranged, and the boys arranged in the group, and the girls arranged in the group, and the teacher arranged in the group. So the total is the 6 ways to arrange the groups times the 1 by 5 factorial by 3 factorial ways to arrange the groups themselves. Multiply that all out, and you get 4,320 different possible poses. Under the consideration that all the girls have to sit together and all the boys have to sit together. If we look at example 2 on page 285, we talk about combination problems in computer science. Suppose there's a set of 10 different data items represented by the first 10 letters of the alphabet, A, B, C, D, E, F, G, H, I, J, to be placed in 4 different memory cells in the computer. First cell has 3 slots. Second cell has 4 slots. Third cell has 2 slots. The last cell has 1 slot. Now, all you're doing is storing things, so it doesn't really matter what order you store them in. 10 items to store. There are 10 choose 3 ways to pick how many things go in the first slot. Once those 3 items have been placed away, you've got 7 items left that you're picking 4 out of to go in here. So those 4 items have been taken out, you've got 3 items left that you're taking 2 out of, and then just 1 way to place that last one. These all have to happen, so you're going to multiply these all together. I hate it when I make a glitch halfway through one of these. 4, 2, 1. 12,600 different ways to store these pieces of data. Ways to store 10 items in these 4 bins. Now you might ask yourself, what if the ordering of these was different? It turns out that it would not actually change things. If I put the 4 slot bin first and switched around with 3 slot, the numbers will actually work out the same. Example 3 on page 286. How many different 5-card hands that contain at most 1 black card can be dealt to one person from a standard deck of playing cards? So we should note standard deck of playing cards has 26 black cards, 26 red cards. We want at most 1 black playing card. So we can break this into cases. In the first case, we have 1 black card, 4 red cards. That means I have to choose 1 black card out of the 26 black cards and 4 red cards out of the 26 red cards. Case 2 has no black cards, 5 red cards. Typically when you see things like at least or at most in one of these statements, you're going to have to break it down into cases. And this would be 26C0 for the black cards, 26C5 for the red cards. We work this out. The number of hands with one card, one black card, we have 388,700. The number with no black cards should be a bit less, 65,780. If it's cases, then either this or this is happening, which means we have to add up. 8, 4, 1, 4, 5, 1. 450,480 hands. There are 484,480 different 5-card hands with at most one black card. Those are just a few different examples of counting problems and working with combinations and permutations to get through them. There are some practice questions on the Google Classroom to go along with this. I do strongly recommend you try as many of those as possible because there are lots of different ways you can use these tools we talked about to count different objects. Right, that's all I have for now. Thanks for watching.